What do we mean when we talk about limits involving infinity? Yeah. Well, the graph functions are always going to infinity. Which part? The domain or the range? Okay. We can look at that, or we can look at it like this. So if like this one, it can go to infinity. Oh, you go plus or minus infinity. Likewise, so can this one. Can you give me an example? Can you give me an example when this one goes to infinity? Give me a function. No, won't go to infinity. How about just x? As x goes to infinity, it goes to infinity. What does this graph look like? It's a diagonal line. So as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive. Okay, how about this one? Now you give me your answer. Now, the smaller x becomes, the larger the function becomes. So this one goes to infinity. So we're looking at, it could mean one of both of those things. So what we're interested in right now is we're interested in this condition. What happens when the function goes to infinity? Why is that important? Well, for example, if we had rational functions as well, if we had the limit of 1 over x as x goes to infinity, what is that limit? What does the graph look like? Right. And if you know the graph, it looks like this. As x goes to infinity, where does y approach? Because it gets lower and lower and lower and lower and infinitely lower and approaches zero but never gets to it. So that's what we're looking at as well. So as x goes to infinity in this function, it goes to zero. But as x goes to zero, the function goes to infinity. The closer we get to zero, the higher the function gets. Let's look at some definitions here. Okay, first one. F of x has a limit L as x approaches infinity. Actually, I say plus or minus infinity. We write it this way. As x approaches plus or minus infinity, f of x has a limit L as x approaches, well, yeah, let's look at this positive infinity and then we'll go to negative infinity. So we could look at it both ways. Okay, now, when we talk about limits, because remember, this is similar to what we've been talking about already in the last couple of sections, one-sided limits. Can we approach negative infinity from the left? No, because negative infinity is already over here. You can't approach it from the left. So this one, by definition, is approaching it from the right. And positive infinity, you can only approach it from the left. So these are one-sided limits with the going towards infinity. Now, how would we relate these to our epsilon delta proofs? So we're saying that f of x has a limit L as x approaches infinity equals that. So for the first one, for every epsilon greater than 0, there is a number, call these m's, we'll call these n's, such that the absolute value of f of x minus L is less than epsilon when epsilon is bigger than m. Epsilon x. When x is bigger than m. So what happens to delta? The reason they're saying f of x minus L absolute value is less than epsilon whenever x is greater than m. What is happening to x in the epsilon delta proof, in the delta proof? Remember what the epsilon delta proof looked like? Let's see. Let's see here. So we have this. This is the epsilon delta proof. So as f of x minus L is less than epsilon for any x. So what happens here is x, c approaches x, or x approaches c, however you want to. Meaning the distance becomes 0. So as the distance becomes 0, x becomes very small. But this m, if x is very small, what does that mean m is? Even smaller. So epsilon itself is a small number. And m, the limit value, becomes even smaller. So we approach 0. The distances get infinitely close and very small. That's what this means. So literally it's going to be the same thing for the second one. For every epsilon greater than 0, there exists an n, a number n, any number n, such that get to an example. So actually, we won't need these because those are proven right here. Remember, we have to prove both directions One coming from the left, one coming from the right. And that's what these are telling us. What's the limit of a constant function? The constant. We know the limit as x approaches infinity, either positive or negative, doesn't matter what. It's a constant function, so it equals a constant. Why? Why is that true? What's the graph of a constant function? Horizontal line. So as x approaches any value c, what's y going to be? That constant function. So that's pretty much a duh. It's always going to approach that value. And then we'll also look at this function, the one we've been looking at. So this one doesn't matter which direction you go to, positive or negative. What's the limit? Nope. Because the bigger the denominator becomes, the smaller the whole number becomes. 1 over 1, 1 over 10, 1 over 100, 1 over 1,000. So the bigger the bottom number is, the smaller the entire function becomes. So let's look at example 1. Show that the limit of 1 over x as x approaches infinity equals 0, and the limit as x approaches negative infinity of 1 over x is also 0. So how do you think we have to prove this mathematically, not graphically? When in doubt, always use the epsilon delta proof. F of x minus L is less than epsilon when x is greater than m. So what is f in this first one? What is f of x? 1 over x. What is L? Limit 0, which means that 1 over x is less than epsilon. So what this proves, remember, whatever x is, so what this proves is 1 over x equals epsilon, which means what? How do we connect these two? So what does x equal? We have to get x by itself. So what does x equal? We just flip them both. So x is equal to 1 over epsilon. But now, because of this, we know that 1 over epsilon is bigger than m. And m itself is getting very, 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 very small. Because here, m is less than x. Let's do example B. Try to prove it the same way. How would you prove it? So that absolute value has to be greater than or less than epsilon. Epsilon is greater than 0 because it's a distance, it's absolute value. What's f of x? This is the function 1 over x. The limit is 0. This one, since it's the negative side, x is less than n. Bless you. So since we're looking at it going to negative infinity, we remove the absolute values. This is what epsilon equals. So what does x equal? Yeah, so x is equal to negative 1 over epsilon. So this condition is true whenever n is equal to negative 1 over epsilon. Now, what are the implications? What does all this stuff really mean? How big is epsilon to begin with? It's pretty small, but it could be as small as you want it. It's how close they're getting. It could be however small you want it. But now look what happens to it. When we go to the negative side, 1 over a small number becomes what? What's 1 over 1/2? Take the top number, leave it alone, flip the bottom. So this will be true for no matter what x we have. X has to be less than n. So we can make epsilon any size we want to. It'll be true. So that's how you prove, again, I apologize, we're going back to the epsilon delta proofs, but that's how you prove, you have nothing else to compare it to. Okay. Limits at infinity. Properties. Are similar to the regular finite limits. What do I mean by finite limits? What are finite limits? And what are the properties we're talking about? Okay, so what are the properties? That's a safe answer, but yes. When we say finite limits, that means X going to a number. So what that means is once you have a number, you plug it in the function and see what happens. So what are some of the properties of finite limits? Any one limit, any one rule. Okay, I'll give you a hint. The limit as X approaches C of F plus G of X equals the limit of F of X plus the limit of G of X. That's the sum rule. Yeah, the sum, the difference, the quotient, the product, the constant multiple. So that's the thing. So the limits at infinity follow the same rules. So we don't have to learn anything different just because it's limits to infinity. Let's look at another example of this. The limit as X approaches infinity of 5 plus 1 over X. And the limit as X approaches negative infinity of pi radical 3 X squared. So what do we do with the first one? How do we solve the first one? Any guesses? What'd you do? Right. So we use the sum rule. We know that the limit as X approaches infinity of 5 plus the limit as X approaches infinity of 1 over X. 5 is a constant, so the limit as X approaches infinity of 5 is 5 plus the limit of 1 over X. As X goes to infinity, this number goes to 0. So the limit is 5. As X goes to negative infinity of pi radical 3 over X squared. So what rule we're going to use here? Which one? Is it a quotient? Well, kind of, yes, but not really a quotient, because a quotient rule has f of x over g of x. It's even, yes, we'll take that as an answer, but there's another rule we're applying here. Does the numerator have an x value in it? No, it's a constant. So what we have here is a constant multiple. because there are no x values in the top. So that's a constant multiple. Now we're looking at the quotient rule. Yes. Where the top is a constant, the bottom is x squared. So as x goes to negative infinity, where does this function go? 0. So we have pi radical 3 times 0 equals 0. So, yeah, actually, so I'll make for you guys, whenever we have properties of functions, I'll make you a little small sheet of them. We'll keep on adding to it as we go through. This is stuff you should be doing, but to help things along. So let's look at limits at infinity of rational functions. So any questions about this one? Because there are no x's on top, I don't have to worry about it. Because the only thing this function is worried about is a function of x. Since there's no function, there's no x on top, it's a constant. Pick it out. You have to remember this rule. A over B is the same thing as A times 1 over B. You can split up fractions that way. It makes life much easier. We're at the beginning of the semester. Where's the calculus in this? The calculus is just using one rule. There's no calculus. It's just a rule. All it's algebra. Everything we're doing is algebra. All right, so let's look at limits at infinity of rational functions. What are rational functions? Is it like this? No, that's called a radical. Rational are fractions. So example 3. The limit as x approaches infinity of 5x squared plus 8x over 3, 3x squared plus 2. So what do we know? What do we do here? We're getting close to defining 3 things we learn in algebra, but we're getting into it slowly this way. You'll see what I'm talking about in a second. So as x goes to infinity, where does this function go? Nope. It's not infinity, it's not 0, it's not, what constant are you talking about? No. The answer is going to be One of the things we can do, especially since we're going to infinity, the first thing we learned about infinity is this. As x goes to infinity, or positive or negative, doesn't matter, this function goes to where? 0. So if we take all of these terms and divide it by the largest exponent, so what is the largest exponent? X squared, right? So let's divide everybody by x squared. You can do that algebraically because are you changing the function? No, you're dividing the top and bottom by the same terms. You're dividing, what you're doing, you're dividing 1 over x squared by 1 over x squared. Okay, let's simplify. So in the first ones, the x squares cancel. We have 8 over x, 3 over x squared. So far, so good. Now, as x goes to infinity, what happens? What happens to this term? Goes to 0. This term goes to 0. This term goes to 0. So all we have left is 5 over 3. Let's look at the next one. The limit as x approaches negative infinity of 2x cubed minus 1, 11x plus 2. So go ahead and work that out and tell me what the answer is. What'd you get? 0 over 2? Is that what you said? Which is what? Anybody agree with that? Yes. The limit is 0. Very good. Not, yes, let's see how you did that. First thing you did is you have a rational function. So you divide each term by the largest exponent, which is x cubed. So we have 11x divided by x cubed, 2 divided by x cubed, 2x cubed over x cubed, 1 over x cubed. So divide each term by the largest exponent. So reduce, so that one's gone. So we have 11 over x squared plus 2 over x cubed. Those cancel, so we have 2. As x goes to negative infinity, this one goes to 0, that one goes to 0. So anything that has an x on it on the bottom goes to 0. So what we have left is, as you said, 0 over 2, which is 0. Very good. So what have we just defined? What did we just look for, and what did we just find from algebra? Because I can tell you, if we switch it, if we looked for x goes to positive infinity, what would be our limit of this one? If we went to positive infinity instead of negative infinity. So if we went to positive infinity of this function, we'd still get 0. And same with a. If we went to negative infinity there, it would give us the answer of 5/3. So what have we just found? Which one? We have just defined what we call the horizontal asymptote. These are the horizontal lines that the function can or cannot cross, but it tapers off to as it goes to infinity or negative infinity. That's a horizontal asymptote. So if we looked at this one the same way we just did the other ones, limit as x goes to infinity, if we did the same thing we just did, if we went 1 over x, x over x, we get 1 over x over 1, which is 0 over 1, which is 0. This one goes to 0. Well, that is our horizontal asymptote. The graph looks like this. And if you want to, I could load up Desmos and we can see what these graphs look like. You want to look at it? Or are you okay? You trust me. But yeah, if you wanted to, you just plug those into the computer and it'll show you the graph, what it looks like. And this first graph on the horizontal line 5/3, the graph's it's going to cross and taper back down, and this side is going to approach it. But it'll never touch that line. It'll never stay constant on that line. It crosses at one time, but then it tapers back down to it. Same thing with the other one. All right, so let's look at a definition of horizontal asymptotes. A horizontal asymptote of the graph of a function, let's say 1/x, is either limit of the function as x approaches infinity, or the limit of a function as x approaches negative infinity, b. You can have 0 or no horizontal asymptotes, 1 horizontal asymptote, or 2 horizontal asymptotes, depending on the function itself. As x goes to positive, negative, infinity. Okay, now, why is it or? Because it all depends on which you're taking it, whether you're taking it x goes to positive infinity or x goes to negative infinity. You can't take them, you can't have an and, you can't take them both at the same time. So you take the positive infinity or you take the negative infinity, it'll give you the same answer. That's the reason it says or there. Example 4. Find the horizontal asymptote of this function. So find that one. Next. So since we have an odd powered function, odd root function, then we have to look at negative x's and positive x's. That'll take care of that because the bottom's always going to be positive. The top can change signs. So when x is negative, we divide each of these terms by the largest exponent or variable. So that becomes one minus 2 over x cubed, 1 plus x cubed, 1 over x cubed. So these go to 0. So our answer is -1. Why is it -1? Because we're looking for the x's less than 0. And likewise, as x goes to positive infinity, we do the same thing. So that becomes 1 minus 2 over x cubed. 1 is a plus on the bottom. Those go to 0. So we have +1 since we're looking at the positive x's. So we have two horizontal asymptotes there. One going to the left, one going to the right. So far, so good? Let's look at example 5. The x-axis, the line y equals 0, is a horizontal asymptote of the graph of e to the x. What does e to the x look like? Yeah. And crosses through 1. So 1, 0, the x-axis is a horizontal asymptote. So we know that the limit as x approaches negative infinity of e to the x is 0. So how would you solve that using epsilon delta? Really can't do anything with this side because our c value is negative infinity. So we look at this side. We have e to the x minus 0 is less than epsilon, which tells us that e to the x is equal to e. as x is less than n, because we're looking at negative infinity. So how do we get x by itself? Because remember, we have to solve for x. Log base what? ln. So this one, x comes out front, so we have ln so our x value equals 1 and less than some value n. What number? 5. Let's look at example 6. A. Find the limit as x approaches infinity of 1 over x. Oh, sine of 1 over x, I'm sorry. And the limit as x approaches negative infinity, or plus or minus negative infinity, plus or minus infinity of sine x, oh, there. So what do we, this is limit as sine 1 over x. So how are we going to approach this one? What would you think?
The limits of sine are 1 and -1.
Or 0? Actually, or it could be any value in between. Because it could be pi over 4, it could be pi over 8. A couple ways you can look at this. If we set x going to infinity, what happens to this value here? It goes to 0. What's the sign of 0? That's one way you could do it. Or we could use substitution. Or let t equals 1 over x. So we have the limit of sine of t as t approaches infinity. So as sine goes to infinity, what do we have there? As no, this one would be to 0. Because as x goes to infinity, this goes to 0. So as t goes to 0, sine of 0 is 0. How about the next one? What does the product rule tell us? Or not? Let's use substitution here again, because we don't really have, we can't really use the product rule here. So if we let t equal 1 over x, what does that give us? So if t is equal to 1 over x, what is x? Flip them. So x is equal to 1 over t. So this gives us the limit as t goes to infinity. No, we have to go to infinity, which with this goes to 0. X is 1 over t sine t. So what's our limit? Why? Yeah. By which theorem? The sandwich theorem. Or the squeeze theorem. Yeah, that's again, I told you earlier, the one we learned a couple weeks back, the sine x over x as x goes to 0 is always going to be 1. It's going to save us a lot of time and effort. Example number 7. Find the limit as x goes to 0 from the left of e to the power 1 over x. Can we do what we just did earlier? We have 1 over x. Have we seen that before? The sine over 1 over x. What do we do when we had that? Bless you. So what does that mean our limit is going to as t goes to what value? If x is going to 0, where is t going? So again, we have x is equal to 1 over t. As x goes to 0, how does this go to 0? What happens? What does t have to do? T has to go to infinity. So as x goes to 0, t goes to infinity, or plus or minus infinity, actually. So e to the power at infinity, actually, we're going to the left side. So it's going to negative infinity. We're going to 0 from the left. That means we're going to the negative infinity. Why does that matter? does the limit of e to the power t as t goes to positive infinity, what is that limit going to be? Think of the graph. E to the x looks like this. As x goes to infinity, where's y going? So it's going to infinity. But since we're going from 0 to the left, from left, we want to look at this side. So that goes to 0. Any questions about that? The sides you're going to, whether it's positive or negative infinity, can affect the answer. 1 over x by itself, as x goes to either positive or negative, is still 0. But when you have an exponential function, it goes to infinity on one side, goes to 0 on the other side. Example 8. Using the sandwich theorem, find the horizontal asymptote of the following curve. Okay, using the sandwich theorem. And no, it's not going to be 3 either. Because what you're thinking about is this. The limit of sine x over x as x approaches 0 is 1. We're looking for the horizontal asymptote, which means we have to go to infinity. We have to look at the limit as x approaches infinity of 2 plus sine x over x. So now we got to think of it another way. So it's we're still going to do the sum rule. This one's no problem. We know what the answer is there. Limits 2, it's a constant function. For this one, we have to use the squeeze theorem or the sandwich theorem. So we have sine x over x. We'll get positive negatives. So we know it's going to be between 0 and 1 over x. Is this a true statement? Because you divided by x, so that's good. So compare the top. What's the largest sine x can be? 1. That's the largest it can be. It can be equal to. Anything else other than that, it's less than. It goes down to 0 and -1. So this is a true statement. As x goes to infinity, what happens to this function? It becomes 0. So sine x over x has to equal what? As x goes to infinity. So be very careful about the sine x over x. If it's going to 0, it's 1. If it's going to infinity, it's 0. Because the graph itself looks like this. It oscillates in the middle part here. It gets up to 1 down to -1. But it crosses at +1. And then it tapers off again. So as it goes to positive infinity and negative infinity, it goes back down to 0. Because the bottom number, sine can only be between 1 and -1. The bottom number gets bigger, so it gets smaller and smaller, smaller, smaller. It's called a dampening effect. The oscillations get dampened. Example 9. Find the limit as x approaches infinity of x minus radical x squared plus 16. Actually, we had something like this not too long ago. So what happens if you just plug in infinity there? X goes to infinity, x squared goes to infinity, square root of x plus 16 goes to infinity, so infinity minus infinity doesn't exist. So what do we do? A good rule of thumb, first thing you want to think about, whenever you have radicals, think of conjugates. What is a conjugate? What is a conjugate? It's where you change the sign in the middle, change the value of it. So I know most of you are thinking, well, why can't we just divide everybody here by the x squared? That only works with rational equations. So good try, but it wouldn't work. The top numbers we have to multiply. So we get x times x is x squared. Positive is positive x radical x squared plus 16. Negative times positive is negative x times radical x squared plus 16. Negative times positive is negative. Radical x plus x squared plus 16 times radical x squared plus 16. X squared plus 16 squared, which those cancel. These middle two terms cancel because they're opposites of each other. So we have inside the parentheses x squared plus 16. We have x squared, distribute that, minus x squared minus 16. Those cancel. So what do we do now? What do we divide by? Because when I got here, the square root of x squared plus 16 squared, the square cancel, and there's a minus in front of it still.
What about the bottom negative?
Which one?
One after
Oh, yeah, it should be a positive. Thank you. So what do we divide by now? We have a rational expression. X is going to infinity. We have. So what do we divide by? What's the largest exponent? X squared. But x squared is inside the square root. So what we have to do is divide each term by square root of x squared. Since that's already inside there. So square root of x squared is x, so this becomes a 1. That becomes a 1. X squared over x squared is 1. So take the limit to infinity. We have 0 over 1 plus square root of 1 plus 0. 0 over 2, which is still 0. All of that for nothing. Because as x goes to infinity, that goes to 0, that goes to 0. We just have 0 over 1. Square root of 1 is 1. 1 plus 1 is 2. Yes. Well, it should be x, but I mean, or square root, because either way, it's just there's more x's on the bottom than the top. This one goes to 0. But yeah, okay, yeah, it should have been square root of x squared, or I combined them both, but incorrectly. Good catch. So you could put just x on the bottom because square root of x squared is x. Right. So that's what's down there. Which is what I did with this one here. X squared square root is just x. X over x is 1. Let's do one more and we'll take a break till tomorrow, Thursday. Actually, let's stop there because we have another type. Remember in algebra, how do you determine horizontal asymptotes? Horizontal asymptotes. How did you determine horizontal asymptotes in algebra? Exponents, very good. So you have a function, r of x. It's made up of the leading terms are the important parts of polynomials. That's all we have to look at is the leading terms. So all we have to look at is the very first term. If the exponent on top is bigger than the exponent on the bottom, what happens? Equals what? If the exponent on top is bigger than the exponent on the bottom. Because if there's more on top, let's say we had x to the 5th over x cubed. Those cancel and those cancel, we have left x squared. As x goes to infinity, it gets even larger. So if the top is bigger than the bottom, then it goes to infinity. If they're equal, then the horizontal asymptote is what? The coefficients. So if we had 3x to the 5th over 5x to the 5th, x to the 5th cancel, leaving just the coefficients. Then if there's more than the bottom than the top, So those cancel, so we have 1 over x squared. As x goes to infinity, this one goes to 0. If there's more on the bottom. But there's one more. If the top is bigger than the bottom by 1, then we have an oblique asymptote or a slant. And with those kind of questions, we have to use long division. And that's what we'll do next time. We'll finish up the chapter or the section and the chapter, because this is the last one. Then we'll jump in chapter 3 and get that taken care of. All right. Any questions?